Hello everyone, my name is Tavan Savun, and here is the brief introduction to tapping ion quantum computer. Before I begin to talk about the quantum computer, let's go to the basic of classical computer. Classical computers use binary digit, or so-called bit, to store the information. One bit can be 1 or 0. The principles are based on binary system. For example, if I want to store the number 3, it can be represented as 1, 1. For larger number, I want more bit, like 310. It can be represented as 100110110. Moreover, we can even represent the letter A and also the letters MSE with bits as well, as seen in the screen. The computers use transistors in order to represent bit. 1 can mean the transistor's electricity is on, and 0 means the transistor electricity is off. These transistors are implanted on the microchip. So this means that the more transistors on the microchip, the more bit we will have, or the more power of calculation we will have. There is the law, namely Moore's law. It states that the number of transistors on microchips will double every 2 years. So the size of transistors will be smaller and smaller and smaller and even smaller until it enters the quantum realm. From this, classical physics can't be used anymore. So why don't we just use quantum principle to implement with the computers? And that is the emergence of quantum computers. Quantum computers use quantum bit, or so-called qubit, to store the information. Different from classical bit, qubit can be both 0 and 1 in the same time, which is called superposition. We will not know whether the bit is 1 or 0 until we observe it. We only know just the probability of each state, denoted by the amplitude square. So, what is the benefit of qubit? Imagine you have 4 bits, 1010. You can only have only one possible answer for one observation. Then you have 4 qubits. Since each one can be both 0 and 1 in the same time, you can have 16 possible answers for one observation. If you have n bits, then you give one possible answer for one observation. But if you have n qubits, it will give you 2 to the power n possible answer for one observation. This will exponentially increase the calculation of the computers. And how to create qubit? There are many types of commonly used platforms, including superconducting qubits, quantum dots, color centers, trapped ions, and topological qubits. I would like to talk about trapped ions. So, how to trap ions? Under the vacuum, the ions are trapped in the middle of the two types of electrodes, which are n-capped electrodes and blade-shaped electrodes. The n-capped electrodes connect to the positive direct current voltage. Therefore, they confine the ion in Z-axis. The blade-shaped electrode will connect to the time-dependent voltage source with a frequency in the range of radio frequency. Let's look through the mechanism of blade-shaped electrodes. The adjacent blades have opposite charge in order to create the electric field to trap the ion. However, maintaining the charge on the electrode like this, resulting to the less stability of the ion. So we need to allow the ion to move in order to release its own energy. So the voltage is swapped like this. And then it is continuously to swap back and swap back like this. Then the ion is unnoticeable. The ion will have unnoticeable motion and can be considered as being tapped in the XY plane. Now, how can we use the trapped ion to be qubits? The electrons have a magnetic property called spin. Spin down is denoted as state 0 or 100% to able to observe state 0. Spin up is denoted as state 1 or 100% to be able to observe state 1. If the spin is in the middle like this, it is a superposition. For example, in this case, we have 36% for state 1 and 64% for state 0. And sure, the ion can be manipulated to be the preferable state of qubits. The qubit is initialized at 0 state since it has lower energy. It is kept under extremely low temperature to eradicate thermal energy since the thermal energy may change the state of the qubit and that reduces the precision of the calculation. After that, the microwave is exerted on the qubit. If the energy of that wave is enough, then the state of the qubit will change from 0 to 1. If it is not enough, then the state will change, but change into the superposition state. That's quite an easy principle. The interesting thing is when more than one qubits are placed close together. If I exert the microwave into the qubit A in a manner that it changes to the superposition state, and later on, I also exert the same amount of microwave that change the state of qubit A on qubit B. Since the qubit A is already in the superposition state, it will cause the superposition between 1 0 and 0 1 state. We will know the state of them, but we will not know the state of them, but we will know exactly that their state must be opposite. This phenomenon is called quantum entanglement. And it is still true if we separate them apart. The quantum entanglement and manipulating of qubits by using microwave are the key basics for development of quantum algorithms, such that we can get more benefit from the qubits interaction. Then, what is the role of material science for the ion trapping quantum computer? Let's see how the device is going to look like. Schematic of ion trapping electrodes, which we see earlier, can be extremely minimized into the microchip and it looks like this. The red metal will be the electrodes for radio frequency, and the yellow metal will be the electrodes for positive direct current voltage source. They are placed on the dielectric material which are above the metal substrate. Single ionized atom which originally has two valence electrons are the common choices. In the aspect of material science, we can improve the performance of chip by concerning about the noise and optimize the material choices. Radio frequency dissipation can heat the chip and create electric field noise. The metals with low resistivity can be used to reduce the effect. Electric field noise from the surface can heat up the ions and disturb their motion. High thermal conductive material such as silicon, sapphire, and alumina can be used to reduce the dissipation. And at last, the stay direct current field from dielectric material can perturb the trap potential. We can solve this by using thick electroplated material layers to reduce this effect. These are the list of references. Thank you for your attention on this video.